Thanks to the organisers for giving me the opportunity to present. So I'll be talking about fair data for the biomolecular simulation community. So I use HPCs, but I don't know much about the compute side of things. But this talk is more about the data that we produce on HPCs and how we can make that fair. So I'm guessing most of you probably know about the data that we produce, but I'll quickly go over. When we perform simulations in our community, we will usually start off with a static structure of a protein, usually from a database available online, like the Protein Data Bank, and then we will perform simulations to sample the interactions and the dynamics of the atoms in these systems. And we want to be able to look at biological functions at atomistic scales when we analyze our simulations. So we produce these trajectories of atoms. We may have hundreds of thousands of atoms in our systems, potentially tens of thousands of snapshots that we're saving, and these may take weeks to perform depending on what infrastructure we're using, and we're producing terabytes of data per simulation. And our community, we will be performing these simulations on national infrastructure, and we're usually allocated this via the HEC Biosim Consortium. So to produce our simulations, we go through various protocols. And here's just an example of kind of the 6 steps involved in performing simulations. And depending on the scientific question you want to answer, what system you're interested in, these 6 steps will look completely different for somebody performing a simulation. So you will get your crystal structure from some sort of database or from an experimentalist working in a lab. You will then need to prepare your system to simulate. So depending on what sort of scientific question you want to answer, you might want to embed a protein into a lipid. You might want to add solvent around that protein to make sure you model its dynamics in solution, neutralize the system, change the pH of the system, and all of this requires different types of software to do this. The next step is to parameterize the system, so to add the physics into it and describing the interactions between atoms. And this step, you might be able to find parameters that are available that somebody has generated previously online, or if you have a type of atom in your system that hasn't been used before, you'll have to create those parameters yourself, so maybe quantum chemistry calculations. So really what I'm trying to say is that when we are performing our simulations, we are using loads of different types of software. It's very difficult to track exactly what we've done when we are performing or setting up these complicated systems. The last 4 steps, so the minimization, equilibration, and the actual simulation, are usually conducted on the same piece of software. So this information will be easier to be able to track because you are using just one piece of software to do this. So minimization, removing the energetic clashes between atoms, equilibration, so getting the temperature and pressure correct, and then performing the simulation. So that's kind of how we are producing our data in this community. What do we do with that data afterwards? And this is something that I think we're not very good at doing, and we need to make our data that we're producing, and we're producing large amounts of data, more fair. And to do that, we need somewhere to share the data. So we need good infrastructure for good quality and widely accessible data. So we have some examples of sharing data. So we can deposit our simulations on Zenodo or Figshare, and there are examples of maybe more biosim-specific databases that you can use or you can access simulations from. But connecting all this data or querying this data, it's just not possible. We can't search for a particular simulation we're interested in from what we currently have at the moment. So in order to be able to search and find a particular simulation you might be interested in analyzing, you need to have a consistent and automated approach to gather that simulation metadata. So some of the metadata is quite easy to provide maybe manually. So say you've performed your simulation and you want to upload your trajectory. You can provide information like the simulation length, what software you've used, what file formats, but there's so much more metadata that you need to reproduce a simulation that you can't provide manually. So we need to be able to collect this metadata automatically while somebody is performing a simulation. We also need to be able to not only share our data at the end once we've completed and published data, but also whilst we're producing the data, so with collaborators and postdocs and teaching as teaching tools as well within our community. And we need to make sure that we can reproduce and validate the published data. So you might have amazing results in a publication producing some fantastic science, but it's often very difficult to go from that publication to reproduce exactly what they've done and get the same results as them. Because people don't usually provide the input files. It's just usually a bit of text saying this is kind of what I've done, but it's just not enough to go through the whole steps again of input files, simulation data, analysis, and then do I get the same results as that publication? So in order to make this reproducible and something we can validate, we need to be able to track all the steps of our complex simulation protocols, as I mentioned before, so our provenance and all of the steps that we take from the initial system to producing the simulation to analysis. And lastly, we need a way to link to other databases, so the biological structures that we use as our starting points to perform simulations. We need a way to integrate with those to have a full provenance of a simulation from start to finish. So in this talk, I'll focus on what we're doing to extract metadata from simulation data and also the data provenance of our simulations. And the work that I'm doing is part of PSDI, which is the Physical Sciences Data Infrastructure Project. And the aims of this project is trying to provide infrastructure that connects experimental and computational data services within the physical sciences. So biomolecular simulations falls under the remit of physical sciences. It's funded by the EPSRC. And we are just one pathfinder in this project. So there are various other pathfinders looking at catalysis, environment, biomolecular science, which is us, and also AI. So now I'll move on to what we are trying to do. So in terms of data provenance, we are using a tool called IEDA, which is a Python infrastructure which helps track complex workflows used in computational science. And it's mainly used in computational material science. And the workflows in material science are usually quite rigid, so you can set up a specific workflow and apply that to many different types of materials, and that workflow stays the same usually. So this isn't the case, as I showed before, for biomolecular simulations. We are all over the place. We're using loads of different tools. So we have created a plugin to IEDA, which is IEDA GROMACS, where you can track the provenance of commands that are submitted with GROMACS. So we want to develop a suite of tools to track the provenance of simulation data, and we started with GROMACS because it's used by 70% of HEC biosim users, but we will be developing more to try and encompass as much of our community as possible and trying to encourage them to save the provenance of their simulation data. So a little bit of the basics about how IEDA works for data provenance. I think if you can provide these 4 pieces of information to IEDA, you should be able to track the provenance of any command. And these 4 things are: what is the command that you want to run? Where do you want to run it? What are your inputs for that command? And what are your outputs? And if you can provide this, I think IEDA is a pretty good tool to use. And this is our example of using IEDA GROMACS to track the provenance of a command in GROMACS. So it sort of wraps, it's a Python wrapper around GROMACS. And what we're trying to do is to stick as much as we can to how simulators currently work, so to not change the culture in the way that they are working. So the command is almost identical to how somebody would perform a GROMACS simulation. The only difference is the underscore. And in the background, you will be able to track the provenance of this command. So in red is the calculations or the command that you've performed. In green are the inputs and outputs for that command. And in blue is the code and where that code sits. So as I said, we're quite messy in this community of what kind of tools we use. So if somebody was using GROMACS to perform their simulations and they might be doing something just outside of GROMACS, we've also included a utility to be able to track commands outside of GROMACS. So this is the generic MD tool. So this example will do exactly the same thing as the previous example, but it's a bit more verbose. So you actually have to explicitly provide the command, the inputs for that command, the outputs, and where the code is. But you can then track the provenance of pretty much any code that you're running on the command line. So here's an example of what that provenance graph would look like for minimizing a protein using GROMACS. And it's just to highlight how you can visualize the inputs and outputs for each of those commands and how they're connected to each other. And if you use AIDA GROMACS then to track that provenance, we know what the inputs and outputs for each of those commands are. So we'll be able to pass those inputs and outputs as well. So the plans are to automate the extraction of metadata with file parsers so that we can create data dictionaries and populate databases for people to then easily be able to search the metadata for how a simulation was performed. Now, the difficulty is, all our simulation tools will use different inputs, have different output files, and this is just an example of what input files look like for AMBER and GROMACS. And the highlighted terms are describing exactly the same thing, but they're different nomenclatures and different units, and we really need a way to standardize this. So we need to develop sort of translation software and come to an agreement of how we describe this metadata across different simulation software. So as I said before, if somebody is uploading their trajectories, they will usually only upload the actual trajectory and then the topology, which describes the atoms in the system. So the inputs and the log files are usually discarded or ignored. That is where all our metadata lies. And if you can use a provenance tool like this, which will track all those inputs and outputs, we can easily automatically extract that metadata. So we do need parsers then for the various file formats, which, provided they don't change so much between software versions, that should be easy to do. But the hard bit is the consensus on the metadata standards and the ontologies that we can produce. So we are working with the code developers to see how we can represent our metadata in a standardized format in this community. I realize I'm going quite fast, but this is what our user environment prototype looks like. So if somebody wanted to use AIDA and AIDA GROMACS, they could just install it in a virtual environment on the computer, and they could run GROMACS on a HPC or on their computer and then track their provenance. And then the idea would be to then upload that provenance online via a web interface. So a little bit more detail on the user environment and actually using AIDA GROMACS, and this is kind of what the workflow would look like if somebody did want to use it. So you'd create your Condo environment, install AIDA and AIDA GROMACS, and then you can start a new project. And AIDA has some command line utilities for you to set up a profile. So this is the Verdi quick step command. And AIDA, you need to start some databases and daemons in the background, and then you can start running your commands as you would normally. So there's a bit of a, it's not completely exactly the same as performing running your commands using GrowMax on its own. So you have a few extra steps that you need to do beforehand, but once you've done those steps, you can then run those commands as you would have done before. And once you've performed all those commands, you can save your provenance into a single AIDA archive file, which is an SQLite format, and then share this file online. So we do also have a prototype for what this online infrastructure will look like. And the idea would be for people to be able to upload their data online. And we have sort of a microservices approach where we have containers for our database, containers for the analysis of simulations, and also containers for any querying that we would like to do. And the idea would then be for researchers to be able to discover this data online, and also we could eventually interface and with external databases like the Protein Data Bank to get a full provenance of simulations. Okay, so there are a few challenges in trying to get all the data provenance of our simulations. So we have quite large files, terabytes in size. So one thing I think we're good at in our community is getting the compute resources to perform these large simulations, but I find it quite difficult of finding where to put that data then. You can't leave it on the high performance computer, you've got to move it somewhere, and you might not have the storage there. And if we want to create this sort of online platform for people to upload their data, we also need the capability of storing all these large files. So the second thing is, I mentioned that you can use AIDA GrowMax on your local computer and then connect to a HPC. This would work if you didn't have two-factor authentication, so I know a lot of HPCs do have this, so at the moment that's kind of not viable to do, so maybe there's a way to be able to run AIDA GrowMax locally and then perform simulations remotely. Maybe that's something anybody can help with. And as I said before, we have different file formats and MD engines, so the difficulty is producing this standard ontology. And lastly is time. So how can we encourage our community to use these provenance tools, because they will benefit them in the future, but when you're doing research, you're just thinking about your results. You're not thinking about how will I reproduce this in 2 years' time. You're not thinking about that. So we need to be able to make these provenance tools as quick and simple for researchers to use. So I realise I'm quite quick, but I'd like to thank you all for your attention and just give a shout out to a few people. So Kin is our industrial placement student, and he's been helping us test this tool. So it's currently in development, but we are trying to get it to work with his coarse grain simulations. And also Joel, Tom and Martin, they want to use simulation data in electron cryomicroscopy, and we are helping them with doing that using our tools. And then also thanks to James, who is the lead investigator of this project, and thank you for listening.